Okay, so welcome to the feedback video for the Practical Geochemistry Data Analysis exam for 2019. What we're going to do, first of all, is just give a quick recap of some general advice that I kind of try and give every year about revision, and then we'll look at the questions later on. So if you want to skip forward a few minutes or so for the questions, then that's great. So try and write new questions every now and then. So those of you who try and just revise answers to past exam questions and learn those, sometimes that causes some problems. So one of the things that I've been trying to get you guys to do is to look through the course, including looking at past papers, and identify topic areas, and then try and write your own kind of questions for those to try and aid your revision, to give you more of a broad sense of what particularly could be asked. There's the kind of the revision exercise that we went through, and also the discussion forum which you can use to do that. To recommend doing those things. And then when it comes to actually answering the specific question of the in the exam, it's important to stay focused on what the question is actually asking. Okay, so sometimes people kind of go off on a tangent of stuff they revised, but doesn't answer the actual question. And I have tended to give some credit for that, but not a lot. Just writing down things are correct. I mean, it's good that you know stuff that's correct, but it'd be much better if you knew stuff that was correct that actually answered the question. So try and identify what the question is asking, and a good way of doing that or practicing that is rewriting the question in your own words. And that also helps you split apart parts of questions which are kind of hidden within each other. So it looks like it's one question, but there are in fact two questions, even in a kind of subdivided question. We'll go on. The first question has got a good example of that. Okay. So moving on to the exam. So the overall mark description, overall mark description of the exam, pretty good this year. Nice wide range of marks. Some people did very, very well, which was great. Some people not so much. Not something to be hugely concerned about for your overall mark for the course. The exam is a small part. The project this semester coming up is much more important and carries a much higher weighting. So if you've not done great, then don't worry about it too much. Likewise, if you've done great, don't rest on your laurels. There's plenty of marks to be won and or lost in the forthcoming weeks, which will be fun. So just looking at the mark distributions for each of the questions. So there's some questions seemingly a little bit easier or more popularly answered, more often answered by students for higher points, and some less so. But overall, some people did well on almost all of the questions, so that's kind of good. And all of the questions, people kind of missing out on marks. So we'll look through these in kind of one by one. And I think I'll do a different video for each of these. So at the moment, we're just going to be looking at question one. So if we look at question one here, so some people, 3 people did very well, 3 people not so well, other people, okay. So let's have a look at the actual question. And this was a question on trace element fractionation. There we go. So the first part of the question is a kind of a good example about reading the question and making sure that you're answering all of the parts of the question. So although this is only worth a kind of trivially small part of the overall marks of the question, kind of 10% of half of the exam, let's have a read of this. So when investigating trace element composition of rocks, why do geochemists normalize the concentrations of rare earth elements to the composition of chondrometeorites? So hopefully you can see that within this question there are in fact 2 questions. There's one, why do geochemists normalize their concentrations, or the concentrations that they measure, not their concentrations anyway. And why do geochemists normalize those concentrations to chondrometeorites? So 2 parts were required to answer that question. And if you just answered, if your answer only had one of those, then you lost a few marks of the small value of marks that this question had. So not a big deal, but why lose them when you can, not? So really what we're looking for here is some kind of statement that there's a lot of variability in the trace element composition or the elemental abundance of even major elements throughout kind of the solar system and the universe beyond. And this large variations in concentration is not really what we're interested in investigating. It's really changes in concentration that are due to processes on Earth. So if we were to just measure the concentrations, those changes in concentrations due to Earth processes would be masked by the presence of all of this variability in the abundance of elements in the solar system. So there's this, I guess, this long-term, not long-term, but from low mass to from low mass to high mass elements, there's a decline in concentration, but there's also this kind of odd, even preference between different elements of being more abundant or less abundant. And if we didn't normalize that away, then that's all we would see in our data. And we use chondritic meteorites to basically we take the concentration we measure in some rock and divide it by the concentration in chondritic meteorites, because the chondritic meteorites are a good estimate of the bulk Earth chemical composition. There are other estimates of kind of bulk composition. So sometimes if you want to normalize to maybe the bulk composition of the continental crust, people normalize to average shale or other kind of geochemical averages. But quite often we use chondritic meteorites because it's a good estimate of the average Earth composition. So then the variability we see in our normalized concentrations will tell us about the processes that have occurred on Earth that have given us differences from that average Earth composition. So that was the first question, and very important to start to realize that you need to be able to pick apart different parts of questions to get the full marks. We all like getting the full marks. Okay, so moving on to another kind of short answer part of this question. So there's this lovely, beautifully drafted figure in the exam, and this part of the question is just asking to define what is this thing on the x-axis? What is the mineral melt distribution coefficient? And there it is. That's what we're looking for. We're looking for an equation that shows us that the mineral melt distribution coefficient, Kd, is equal to the concentration of that element in the solid phase, in the solid mineral, divided by the concentration in the coexisting liquid. And you could have had a bit of text to explain what each of these parameters were. That would be kind of great. That's all we're looking for in that part. So moving on to kind of the bulk of this question, so the next kind of few parts all kind of like go together to lead you through not necessarily a calculation, but a process which allows us to model how these elements might change in their concentrations as different processes occur. So the question asks if we have a source rock that has a bunch of different minerals in it, some olivines, some orthopyroxenes, and plagioclase. We're basically asking you to estimate the bulk distribution coefficient. So that the figure is showing us the mineral melt distribution coefficients. So we're asking now to calculate the bulk distribution coefficients for two of these elements, for lanthanum and ytterbium. To show you workings, but I put that in just in case you didn't think you had to show you workings in an exam question, which should be fairly obvious, but I'll put it in because point you towards where the marks are held. So this is the kind of the broadly kind of the equation that we're looking to use in this case here. So the bulk distribution coefficient D. Now I've also written that it's equal to Kd, which is actually not this Kd. I mentioned this in the lectures that sometimes the terminology or the symbols used for bulk distribution coefficient can sometimes be in some literature be Kd. Sometimes I think in quarters and other literature might be just capital D. But whichever one you use, it doesn't really matter as long as you know what you're clear about what you're talking about. We're taking the mineral melt distribution coefficient, that's this part here, so that's the concentration in the solid phase, phase J, so J is the different mineral, divided by the liquid concentration, times the proportion of each of these kind of solid phases. So just go through and explain in a little bit more detail with the actual numbers. So we're asking you to read off the graph. What are the mineral melt distribution coefficients for lanthanum? So we've got the olivine one here, that's 0.00001, orthoperoxine 0.005, and plagioclase 0.08. And then read them off similarly for ytterbium over here. These are the numbers that I have read off. You didn't have to get these exactly as I've got them, as long as they were broadly, sensibly and could have conceivably be read off the graph. Remembering that this is a logarithmic graph, so you need to be fine. So 0.5 isn't halfway between 0.1 and 1. But I guess that was made easier by the lines that I drew across there for you. And then we just plug those numbers along with the proportions into the equation for D, and that's what's shown here. So we've got the proportion of olivine, 0.6, 60%, 0.6, times the mineral melt distribution coefficient for olivine, plus that for orthoperoxine, 35% times 0.005, and you plug your numbers in and you get to your answer. So that's pretty standard, straightforward stuff. Would have got you almost all the marks. It would have been worth just making a note, explicitly asking for here, but just noting that both of these elements have got bulk distribution coefficients that are less than 1. Okay, so these are both incompatible elements, and lanthanum is more incompatible than ytterbium. Okay, so this will feed into the next part of the old question, Rooney. So before we get on to the next kind of calculation / estimation part of the question, we were asked why we have these different KD values, mineral melt distribution coefficients for the different elements. So specifically, this question is asking for the systematic trend in distribution coefficient from lanthanum to ytterbium for the mineral olivine. So it's asking for this red line here. Why is this red line like this? Why is there a lower mineral melt distribution coefficient for lanthanum than there is for ytterbium? Why does it increase as you go from light to heavy rare earth elements? So to answer that question, you could have maybe rewritten it in your own kind of words. First of all, why is the rare earth elements incompatible? So why is this part of the graph down here and not kind of up here? Why are these numbers all below 1? What is it that the rare earth elements are actually substituting for in olivine? Okay, so what element are they exchanging for, which is effectively making them incompatible? And how are those elements different to the rare earth elements? So the substituting and the substitutee, the one going in, the one coming out, how are they different in terms of their charge and their size? And then you can apply the Goldschmidt rules from the lecture to explain why one kind of element might be more incompatible than the other. Okay, and hopefully you'll have remembered from the lectures that and also from geomaterials and geological training so far, that in olivine we are looking at magnesium and iron in 2+ coordination 2+ valence, and the rare earth elements are almost all 3+, but they're much heavier, so their sizes are somewhat similar. So they can substitute in, but not very well, which is why they are incompatible. Okay, and also looking at this, we can see that there's this trend from light to heavy rare earth. So there's a systematic change in the size of these elements, and you might want to look at which way around that is and why that is. Why is there a size difference? Because that could have allowed you to expand on your answer a little bit, get a bit more extra marks. So that's what we're kind of looking for in part D. So going back to kind of the rest of the question. So we have calculated some KD values in part C, I think, for lanthanum and ytterbium, so bulk distribution coefficients, or big D. Now, the question here, part E, asks if we take that rock that had the 60% olivine, 35% thingy, and the rest of it, some other stuff. If we take that rock and we were to melt that by 1%, okay, so we were to take it, melt it, and then produce 1% of that initial rock was melt, what would the rare earth element concentrations look like in that melt? That's what the question asks. And then it gives you more information here that we can assume that the source rock has the same rare earth element composition as the bulk earth. So let's have a look about what we're going to do. So we can carry over from part C. We've got these two incompatible elements, but lanthanum is more incompatible than ytterbium. So without even doing any calculations or anything like that, we know that the concentrations in the melt should be high for both of these elements because they're both incompatible. So these elements should be enriched in the melt, and lanthanum should be more enriched than ytterbium because it is more incompatible. So we should have a high concentration for lanthanum and a high but not quite as high concentration for ytterbium. So that without doing any kind of calculations or anything like that, we can kind of know that already. Okay, so one is more, they're both incompatible, one is more than the other. Okay. Now you could calculate how much the concentration will change if you wanted to. People did do this, which was great. So looking at this this equation up here, so this is telling us the concentration in the melt, the liquid, divided by the concentration in the kind of original unmelted rock. So that basically the ratio of enrichment or depletion is equal to this equation here, which we showed in the lectures. And we can plug in the numbers that we know. So our F, our fraction of melt, is 1%, so 0.01 here, and we can just plug in our big D for the different elements here. And this gives us for lanthanum 64, so its concentration should be 64 times what it was in the original rock in the melt, and it should be 28 times higher for ytterbium. So that fits with what we thought from just knowing that they're incompatible. So these numbers are high, they're bigger than 1, and the lanthanum is higher still. So a few people used this figure here to show this, which was great. So at a low degree melt, okay, the more incompatible elements will be up here, the slightly less incompatible elements will be so looking at making a sketch of this, so a sketch of the expected rare earth element concentrations normalized to contracts. So what I've got here is a graph of kind of what I was really kind of expecting. So we've got along the bottom the rare earth elements. So these are basically given in the figure in the question. And then we've got the concentration in the resultant melt, normalized to the contract concentration. So this is the concentration in the melt divided by the concentration in contracts. So if we have a source rock that has the same composition as the bulk earth, so we can then assume that it should have roughly the same concentration as the chondrites. Then if we take that concentration and divide it by the concentration in chondrites, then we should get 1. And that's what's shown by this red line here. So I didn't ask you to draw this red line, but this is just to point out that this is where our starting kind of source rock normalized concentration would be. And then you could have done these calculations, but even without doing them, knowing that the lanthanum concentration and the ytterbium concentration will be higher up here somewhere, and the lanthanum concentration should be higher than the ytterbium concentration. So you should get like at least these 2 points on here and a kind of slope between them. You could have worked out the bulk distribution coefficient for every element and plotted where they were, but because there's such a systematic change between lanthanum and ytterbium, we can assume that they will plot on that straight line. Now there is one exception to that, and if we look at the mineral melt distribution coefficients, you can see that there's a systematic change for for olivine here and a systematic change for orthopyroxene. So we might expect there to be a smooth change between the bulk distribution coefficients and therefore the melt composition of this. But if we look at plagioclase, there is this anomaly at the element europium, where in the mineral plagioclase, europium is almost compatible. It's slightly incompatible, but it's almost compatible, which means that even though we've only got a small component of plagioclase in our rock, the bulk distribution coefficient will be higher in for europium than for the other rare earth elements. So that means that when you could calculate it, you wouldn't expect this for the exam, but you might want to note that for europium, the concentration in the resultant melt should be a little bit lower. So this profile looks a bit like this. So that's what we're really looking for part E. And then part F is just asking you to, on that sketch, what would the concentration of that melt be if the percentage melt was increased to 10%? So without doing any calculations, we can just think about what that would mean. So if we have 1% melt of an incompatible element, then almost all of that element will have gone into the melt, leaving the resultant stuff that's left behind, the 99% of the remaining rock, that will be relatively depleted in those rare earth elements, those incompatible elements. So when we melt more, so we melt from 1% to 10%, we'll be melting rock that has got a very low concentration of those elements. So even though we will be preferentially adding these trace elements to the melt from our remaining solid rock, that solid rock didn't start off with much in it. So we're effectively diluting our initial enrichment in these trace elements. So you should have something that looks a little bit like this, where we have basically lower concentrations for lanthanum and ytterbium, a lower slope between them than up here, but the overall the same features. We're just diluting it down. Now you could have plugged the numbers in to the equation from before if you so chose, and you can see that we do in fact have lower enrichments, but still enrichment, and there is still a slight preference for but a slight enrichment of lanthanum over ytterbium, but not as pronounced as for that low degree melt. So those are the things we're looking for in that really part of the question and answer. Okay, so that was question 1. So again, some people did really well on this. Some people just missed out a little bit, really understanding what we were looking for in the answers. But overall, a good job. Right. So for the rest of the questions, 2, 3, 4, and 5. There's no question 5, just 2, 3, 4. I'll do some other videos because this one's already got on for far too long. So we're gonna. So